Um, hey everyone, welcome to another installment of LlamaIndex webinar series. Today we have Sepanta, the first author of Nudge, lightweight non-parametric fine-tuning of embeddings for retrieval. So as context for retrieval augmented generation, the quality of the embedding is super important to be able to get back accurate context for any kind of agent-based applications. So Sepenta will describe a novel method in kind of fine-tuning non-parametric embeddings to further improve these retrieval and tell us a little bit more about how that works and how that impacts sort of application performance. So with that being said, Sepenta, feel free to take us away.
Thank you, Simon, for the introduction, and thanks a lot, guys, for having me here. I'm very excited to share the work we did, and hopefully get people to use it more. Hopefully improve the RAG pipelines that Simon mentioned. So yes, as Simon already introduced me, I'm Sepanta Sep. I'm a postdoc at UC Berkeley, and I'm going to present the work I did with Zach Welmer and Aditya Parameswaran here at Berkeley on fine-tuning embeddings for retrieval. So as you guys probably already know, there is a common retrieval method often people use in industry and practice is k-nearest neighbor retrieval. People use it in RAG pipeline. It's often more efficient than other retrieval paradigms, and it roughly works as follows. We have a text corpus. We have a bunch of documents, and we divide up these documents into smaller chunks, and we input these little chunks of documents to an embedding model. So embedding model takes documents as input and gives us a new vector in high dimensions. This vector kind of embeds our text input into a high dimensional space. And we do this for all of our text embeddings, and we store them in some vector store. So here on the right, I'm showing an example of what it would look. The embeddings are just vectors. Here I'm showing it in 2 dimensions. And hopefully they capture semantics about our data, and we can only use these vectors to actually do any search over our data. The way we actually do the search is that we get a query, and then we give the query to an embedding model. And let's say the query now is a new vector. It falls somewhere in here. And then we just do a basic nearest neighbor search. So we find the top k closest elements to this vector within the data embeddings we already have. And so here, let's say we retrieve top 2 results. And so it's going to be these results. And we just do a basic lookup nearest neighbor search from our vector store. It's usually simple and efficient, and get the result. And so this is great. This is pretty simple. Often you can use pre-trained embedding models. The retrieval part itself is pretty efficient too. It's simple, easy to set up, and it often works. The problem, however, is that it sometimes doesn't. You might miss the relevant record. So in this specific example, for example, we could have had the ground truth be this other data embedding data record that we actually didn't retrieve. And so it's often possible that you miss out on relevant documents when you just do these simple nearest neighbor lookup. I'm showing an example of why this often happens in practice. So here we have this question. I've taken it from some benchmark, but the question is, how chemically contaminated are we? And the goal is to retrieve medical documents that relate or somehow support or answer this question. One ground truth medical document is what I'm showing it here, and it talks about how meat is involved in bladder cancer, and there is meat-related problems in when you cook and process and stuff. And so there's all these other information about things that are not really existent in the query. Even if they're relevant to the query, they're not really semantically equivalent. So there's always going to be this semantic gap between the query itself and the documents we're trying to retrieve. So there's going to be some gap between the two, and so that can cause problems if this gap is too large when we are retrieving items. Another problem is that we often have domain-specific vocabulary in our data set. So there might be this chemical, but the model doesn't actually know that this is a chemical, and we're just going to not be able to get the answer correctly because the model doesn't have enough knowledge. And beyond all these, there is, in addition, just inaccuracies in the embedding model. So the embedding model might just not do a good job on some data records. So it might just be bad embeddings. And at that point, then doing a similarity search might not do a great job. A solution to all these problems is often trying to improve the embeddings. And this is done by fine-tuning the embeddings or the embedding models. This intuitively means that we can kind of just change these embedding space so that hopefully things that are actually correct will be closer to each other. So hopefully, for example, this ground truth answer would be closer to the actual query embed. And the goal is going to be that if I actually now answer similar queries on this dataset, so I somehow knew that the ground truth answer to this query is this document, then I ask a similar query, I should be able to get the correct answer next time. So that the model hopefully can learn that this is the answer, and then from that, we can just ask more questions on our documents, and hopefully the model can improve, at least for the specific document and query workload that we have and we're interested in. And so you can kind of see this as bridging the semantic gap for the specific data set in hand. So we're not trying to give a better model that works well for every possible text or query workloads, but we're saying that, oh, I have this data set and I want things to be better on this specific data set. I don't want to get this query wrong, and we can try to actually make things work in this specific data set through fine-tuning. People have done fine-tuning and previously. There's two common approaches to fine-tuning. One standard way of doing it is just fine-tuning the embedding. So we had the embedding model, we just modify the parameters of the model. Hopefully it gets better, it gets smarter, and works well in our specific data. An alternative people often use is training adaptor models. These models modify the output of the embedding model itself. So it changes the pipeline slightly. We had this text corpus that would go to the embedding model. Now we're adding an adapter on top of the embedding model. So adapter, you can see it as a transformation. It takes the original vectors and just transforms it to a new vector. And then we store these vectors that we get from the adapter in the vector database, or we use them as query embeddings, and so on. So we learn a new model that kind of tries to adapt the original pre-trained embeddings to our specific data. I'm going to call both of these approaches parametric, which means these approaches modify model parameters to change the embedding. So fine-tuning the embedding model modifies the parameters of the embedding model itself. Training adapters modifies the parameters of a new adapter model that we learn. And people have used these, but neither of them actually work that great for practical purposes. If you're fine-tuning the embedding model, it's going to take a lot of time and computational resources. So it's going to take hours often to just fine-tune your model for your own data set. And even after you fine-tune, you have to re-embed the entire corpus. So it's going to take a while to just go over your entire corpus, do a model inference if your corpus is large, to re-embed everything. And in addition to all this, you actually need to have enough computational resources to do this. So if you wanted to do it locally in your computer, you need to have large GPUs, perhaps multiple GPUs, depending on the model you're using, to actually be able to do this. It needs access to the model parameters. So you can't actually do this with OpenAI models because they don't give an API and you don't know what the model parameters. So it's not applicable to every possible model. And in addition to all these, you're going to have extra hosting and maintenance costs. So you have to deploy this model that you fine-tuned. It's different from the original model. So it might cost you more to actually deploy it somewhere. You can't just use the same pre-trained model everyone else uses. And even after that, you might need to retrain it over time as you get more data, and you have to figure out how you want to retrain it. There's going to be extra costs associated to retraining. And it's not even obvious how you should do it because you need to make sure the model doesn't forget about the old data set. So you have to kind of balance retraining with including previous information you had, and it's not obvious. It's just extra headache to have to deal with. On the other hand, we have these training adapters, which address some of these issues. We have, they're usually more efficient. So these models are typically small. You can have a linear model that does this, so it's easy to train. There's efficient. It also doesn't need access to model parameters because it just works on top of this model. So it kind of looks at this model as a black box, takes the embedding, and just learns the transformation on top of the embedding. So this is good. It's you can do it for all models and kind of efficiently, but the problem is that they don't actually do much. Often we have a few percentage point improvement in accuracy if we use these models. It's okay, you can use them, but there's also just extra hosting and maintenance costs. So you actually have to host them still somewhere. There's this extra inference you have to do when you do a model embedding. So you have to actually do a model inference here. And in addition to that, you still have to deal with the insertions. So if you have new insertions, you have to retrain the model and you have to figure out how it's possible to do that. So to summarize, there's no approach currently existing that is efficient, effective, easy to use. You can just plug it into any model, any embedding, any RAG pipeline you have, and just get accuracy boost for your specific data. Until Nudge. So Nudge is our proposed approach. It's a lightweight, non-parametric fine-tuning method. We call it lightweight and non-parametric because it actually just modifies the embeddings themselves, not the model parameters. So we're not learning a new model, we're not training models, we're just modifying the embeddings. And it turns out by just doing that, we can provide accuracy boost by at least 10% across various data sets that we tried. So it provides extremely high improvement in accuracy. We also saw no auto distribution regression. So if you get moved to a new query workload, there's going to be no regression based on the model performance. You can get this very efficiently. So it runs in minutes on CPU. It does not require any corpus re-embedding after you fine-tune your data. And there's no extra model inference at test time. So you basically get this significant accuracy boost by spending very little amount of effort on fine-tuning your embeddings. It's model agnostic. You don't need to actually know what the model parameters are. It works well with closed source model. You can just plug it in if you have an OpenAI pipeline, just plug it in directly and get the accuracy boost in a few minutes. And finally, it's very low maintenance. So you can do insertions in it very efficiently. It's easy support for insertions, and there's no model, so no model hosting cost at all. So there's no extra cost for hosting your model. You had your embeddings, we just modified them, and things are just suddenly a lot better. So this is kind of my sales pitch for why you guys should use Nudge. It's a very simple, lightweight, efficient method, and works well in practice. I am going to go a little deeper on how it actually works and what it does in the rest of this presentation, and I'll also present results on supporting these claims experimentally based on baseline experiments with it. So at a high level, Nudge just solves a constraint optimization to change the embeddings. So I'm going to go back to the example we had earlier. We have this data embedding, we had some query here, and the goal was that the ground truth answer to this query is this data embedding, but we want to, but when we answer this query from our vector store, it's going to tell us these two are the ground truth answers. So we're missing out on this. Intuitively, what we would want to do is that we kind of just want to nudge this embedding closer to the query embedding. So that now if I just move this here and I ask this query, now it's going to give me the correct answer. You can kind of see this as an update vector. So we had this original embedding here, and I'm just adding a new vector to it that moves the embedding to this new location. So I'm just going to denote this update vector with some value delta. And hopefully after I do this update, so it's just a vector addition, after I do that, I'm just going to get a new vector that is better and closer to my query. The problem, however, is that if I do this and move this so much, then I get a test query, and let's say this test query is somewhere down here. And now I'm going to answer this one wrong, because this test query is now going to be answered by this one, but the ground truth answer was the original embedding that we had. So you can kind of see this as a problem of overfitting. If I move my embeddings too much towards my training queries, then I'm just going to overfit to my training queries and answer my test queries wrong. So hopefully what I would want to do is to be somewhere in between. To kind of get the best of both worlds, that I want to have move towards the training query, but I want to stay true to my original embedding at the same time. And I can do this by ensuring that the embedding only moves within some constrained region. So I'm just going to define this area, let's say, around the original embedding that was here. And I'm going to say that, oh, move this data embedding towards the training query, but don't do it too much. Do it within this region I defined. And so this avoids overfitting to that specific training query we had. And it just doesn't distort the semantics that we had in the pre-trained embedding. So we're kind of still staying true to the pre-trained embeddings, but we're leveraging this new information we got, which is this data is actually the ground truth answer to this query. So we're taking into account that information, but the constraint ensures that we are not doing it too much. And hopefully this makes sure that we still get the correct ground truth answer if we get new test queries. More specifically, you can see nudge as following these two general steps. We're trying to maximize the similarity between queries and their ground truth answer, and we want to do that within a constrained region. I'm presenting a broader picture of what actually happens here on the right. So here we have initial data embeddings, which are these circles here, same as before. So all these are the initial data embeddings. They're colored the same as the training queries for which they're the ground truth answer. So this is the training query, and we have these two data embeddings that are the ground truth answer for this training query. This data embedding is the ground truth answer for this training query and this one as well. This data embedding is the ground truth answer for this, and so on. And what we want to do is that we want to move these data embeddings towards the training query. So for all these, we want to move them towards the training query. And we want to do that while staying within a constrained region we defined for fine-tuning. So we have this constrained region, and we're saying that the fine-tuned embeddings, so in this case, these stars that I've denoted, are not going to be outside of this constraints. You can formulate this as a constraint optimization problem. We are not learning any new model parameters or adapters to actually do this at all. We're just saying this data embedding actually should be here. So I'm just modifying the data embedding. It's a simple vector addition. So I'm just learning a new vector that moves this by this amount to this new location. And I'm saying that this is the new data embeddings for this specific data record. Depending on how you actually solve this constraint optimization problem, we can get different nudge variants. So we can maximize it differently. We can use iterative method or do it in closed form. Depending on the constrained region you define, you can also get different nudge variants. So I'll go through different possibilities, but there's different ways I can set up this constraint where I want my embedding to fall within. I'm going to talk about one specific variant here, which is called nudge n. There is other variants. You can look at the paper for more details if you're interested, but nudge n is the main variant that actually works well in practice and is very efficient and simple. And so by default, we encourage everyone to just use that variant. So what does nudge n do? As I mentioned, we had these data embeddings. We wanted to move them towards the training query, and we want to stay within a constrained region. So nudge n just defines this constrained region as follows. We have two specific constraints that nudge n defines. The first one is that we want to make sure the embeddings are normalized. So normalization, I'm showing it in 3 dimensions because it's easier, but it basically means that the embeddings fall on the unit ball. So I want to make sure that if this is the one norm Euclidean ball, so this is in 3 dimensions, anything on the ball is going to be normalized. And it means that I just want to make sure that my embeddings stay there. They don't move outside of this surface of this ball. So this is the original embedding and my training query, and this new fine-tuned embedding has to be somewhere on the ball. I want to also make sure that the embedding changed by at most by a parameter gamma. So I have another parameter, another constraint that says the new embedding isn't going to move outside of this radius gamma from my original embedding. So that kind of defines another ball centered around the initial embedding. So we want to make sure that these two constraints are satisfied at the same time while we move towards the training query. We also want to set this gamma somehow, and this gamma is set by maximizing validation accuracy. So you can kind of see this as like a bi-level optimization problem. You're first moving data embeddings towards the training queries within these two constraints. And then at the same time, we're setting gamma to maximize validation accuracy. Turns out you can actually solve this whole optimization problem in closed form very efficiently. I'll give a little bit of details on how this actually works and how we can solve the problem. This specific variant is called nudge n because n stands for normalized. There's going to be some other variant I'll talk briefly about that ignores this normalization constraint. So what does actually the solution look like? Here is an overview of what happens under the hood if you just called nudge on your embeddings. So let's say we have a bunch of training queries, and here they're all on the unit ball because we want everything to be normalized. And we have some initial data embedding here, and we're trying to fine-tune this based on these based on these queries. So these queries, their ground truth answer is this embedding. And what we are going to do is that we can just normalize the training queries we had and get this normalized average of the queries. So we have average of the queries, and then we're normalizing it. It's going to be somewhere on the unit ball. And what nudge is going to do is that it's going to find some trajectory on this unit ball and move the initial data embeddings towards this normalized average. It's only going to move it by gamma. So it's just going to move on this ball up until this parameter gamma that we had. And it's just going to say this new location I ended up with is the fine-tuned embedding. There is actually an update formula for how you can do this. So I can just come up with a formula that is a vector addition and just gives me this new point. So I don't really need to think too much about it. I can just do this vector addition across all embeddings. So here I'm just showing one example, but I can find what this vector is in closed form for all possible data embeddings that I have in my data set. So I can just apply it to all of them, and it just becomes a simple matrix addition. I can also find gamma optimally. So I can figure out how much I should be moving this based on my validation set optimally. So I don't need to do much either. I don't need to necessarily do a grid search. And I can do all these in time equivalent to almost equivalent to a training and validation iteration of parametric methods. So it just takes basically a single pass over my training and validation data to do all of this. And at the end of that single pass, I'm just going to end up with these new embeddings. So this is cool. It's efficient. There's a bunch of math behind how we should actually move the embeddings and what's the best optimal way of doing it is. So let's see how it actually works in practice. So here I'm showing some of our results that we have in the paper. I refer you for more results to the paper. The results here average across 7 standard text benchmarks. They're taken from bare or killed data sets. The result I'm reporting is going to be average across the 7s. The details for a specific data set is in the paper. And I'm going to report recall at k, it's denoted by R at k. We also have NDCG, normalized discounted cumulative gain, which is another common retrieval metric people use. On the left side, we have a bunch of different fine-tuning methods. PTFT is just fine-tuning the pre-trained model parameter itself. Adaptor is the adaptor method I talked about. Nudge n is the method I presented, and nudge m is very similar to nudge n, but doesn't have the normal constraint on normalized embedding. So you can have embedding that are not normalized. And then each of these groups refers to a specific embedding model. So we have BGES, which is a 33 million parameter model. It has the smallest embedding dimension. Then GTL is the larger embedding model. It has more parameters and higher embedding dimension. And this last one, T3L, is the OpenAI's text embedding large 3. It has the largest embedding dimension. The first thing you can see is that nudge actually provides significant accuracy boosts across these models and datasets. So we have around 10% or more improvement in average NDCG. You can compare that with adaptor and PTFT. So they only give you a few percentage point improvements in accuracy, so not much. While nudge n is significantly better in terms of improving the accuracy. I also just want to point out that you cannot even run PTFT fine-tuning the full pre-trained model in GTL on a single GPU. So we had one A100 GPU, and you just run out of memory if you're trying to run this. And you cannot run it on the OpenAI embedding model because it's closed source, and OpenAI doesn't give you an API to do that. So you get a bunch of accuracy improvement, and you can get this actually in a matter of a few minutes. So here I'm showing the run times for obtaining these results on BGES. So the fine tuning time to actually obtain these numbers that I just showed. And nudge N only takes around 11 minutes, while PTFT takes hours on a GPU. An adapter is fast on GPU, but still takes more than an hour on a CPU. So, but nudge takes up to 11 minutes, and that's on a CPU, and in a couple minutes if you run it on a GPU. So runs within minutes even on CPU and is pretty efficient. So to conclude, I have presented Nudge. It runs in minutes, provides significant accuracy boost. It fine-tunes the embedding by solving some constraint optimization problem. It's a non-parametric methods, which is an interesting and novel way to think about how we can actually improve pre-trained models, because we don't actually need to modify the parameters necessarily. We can actually just optimize the output of the model and get significant accuracy boost. So it's also an intellectually interesting direction. You can try it out in LlamaIndex. It's already integrated, very easy to include into your RAG pipelines. You can just add it in after you embed the corpus at ingestion time. So after you get the embeddings, before putting it in your vector store, you can just call nudge, and it's just gonna give you a little accuracy boost on your embeddings. Please, I'm excited to hear if you do use it. Let me know. If you don't use it, also let me know. I want to hear about your use cases and where it worked, where it didn't work. So would be happy to chat more about any potential use case that you guys have. And thank you for listening, and I am happy to take more questions.
Awesome. Thank you so much. That was a fantastic presentation and definitely really showcase sort of how novel this approach is and how much of a performance boost and in terms of accuracy and training costs it is compared to the existing methods. Maybe I'll kick off the Q&A just with some initial questions. And for anyone in the audience, please feel free to drop your question in the chat, and then we'll try to get through that later as well. I think there's two perspectives which I would really love to understand a little bit more. One is from like a practitioner perspective of using this in production and powering RAG and agent use cases. And number two is sort of like the researcher perspective of how to understand where to go further from this and what are the different areas that could be improved upon this. So let's start with like a practitioner perspective, right? So you talked about the performance characteristic quite a lot. I want to understand a little bit about, how this system will look like when you're dealing with different sizes of data, how that will impact sort of the time it takes to train and just generally the scaling considerations. So that's number one. And I think number two, we'll have to understand a little bit about how you would think about like changing corpus of data, what that process will look like in using the system.
Yeah, that's a good question. So the first point regarding how it would look for example, size of data. One of the first thing I would want to say is that the fine-tuning time does not really depend on the corpus size. It depends on the number of training queries you have. So if you have more training queries, it is going to take longer to train. So if you have larger corpus, you better have larger training queries, because that's where you would, if you don't cover that many queries on your data set, then you're probably not going to get that much benefit. But yeah, so it's basically, I want to say the training time is just proportional to the number of queries you have. Because you can parallelize this so easily, and you can just do it, it becomes like a matrix addition. The size of this matrix is similar to the number of queries you have. And so that matrix addition, as long as you can parallelize it, that's okay. But related to the scale, I think that's a related point, which is if you have a lot of data, you can't probably actually just load it in memory anyways. So you actually need to be careful how you handle your data size and how you actually build systems around this. So you kind of, for example, you might want to do it in batches, bring some of the data set, and then do fine tuning and then move it back. The good thing about Nudge is that it doesn't require to do everything at once. So you can actually just fine tune it on some of your data, update the embedding on that, and then move on to the next batch of your data. And so this is pretty cool. And this is also a difference between parametric methods, because with parametric method, you can't just divide it up into, oh, now I want to do this part of data, and then I can move on to this other part, because you're learning a single model for the whole thing. But because here we're not actually learning a model, we're just modifying the embedding model, the embedding parameters themselves, the embedding vectors themselves, you can actually just do it in batches. So if your data set is actually way too large and you can't just bring it all in memory at once, you can still do this. You just got to divide it up in batches, which is, I think, another advantage of the method. What was the second question?
Yeah, I think you roughly touched on it already as well. It's
Okay.
about like changing data, right? So I think in production, oftentimes the knowledge corpus could be updated across time, right? So just curious about how you would think about that scenario. Like, would you, like, what are the right approaches to think about this continuous tuning or training in that kind of
Oh,
situation?
yes. Yeah. So I think the good thing about this is that, yeah, as I was, I guess, kind of said briefly, is that because you can divide up the training process and it doesn't have to be everything at once, you don't have to worry about how things change. You can, like, every time you get new data, you can technically just run this on your new data set that you got. So it's very easy to just break it up and do it as you get. So I think very easily you can just have a nudge part in your ingestion pipeline. So if you have like data ingestion, every time you get new data, it goes through some ingestion pipeline, I'm guessing, to get embedded and everything. And so at the same time, you can also just apply nudge on it, and you don't have to worry about how it interacts with the old data set as much. One thing I think I should mention is you need to have training queries. So that's one of the things that you actually need to worry about a little more, which is how do I actually get how do I get training data to do this? And I know LlamaIndex is a way of generating synthetic queries, which I think is helpful. So you can just generate queries based on your data using an LLM and use those for fine tuning. I think you can also store these queries as you have a RAG pipeline. So if you see more queries, you can just store them and then apply them for fine tuning later on, so you can kind of know what the query workload that the user is interested in. But that is building a pipeline around an ecosystem around the queries. I think that's important. That needs more work, I believe, within the system.
Totally. Yeah, maybe just one quick remark for clarification. I think there's two things that could come in after the initial like document embedding as well as fine tuning, right? So sort of the knowledge base of document corpus itself could change. We can get new queries and new label data in terms of like what is the question and then what is the correct retrieval target. And I think like the former, we can directly embed it and kind of my understanding is that nut will not influence those. And then for any new like sort of ground truth training data set, you can continuously like improve the system without having to worry about like full retraining, right?
Yes.
So this makes a lot of sense. I think there's a question from the audience about like what is the recommended number of training queries, right? I think that's a pretty important question. Like given if you have a very, very massive document corpus and you have a very small number of like ground truth pairs, I guess you can only nudge a couple of the ground truth vectors, right? So how do you think about that ratio and the effectiveness of that or generalization across the whole document corpus?
So one thing I want to say is that in a lot of the benchmarks that we see is that, and I believe this is generally true in like a common observed phenomenon in practice, which is even though you often have a very large corpus, people actually usually ask about a small fraction of it. And so in those cases, you actually don't need to have training queries for things people don't ask. So if what really matters is like the proportion of documents that are being hit and by the user queries, and you kind of want to have, like, I don't know, a few queries for those documents. So when I say a few, like for each like passage that's answered by the user, you probably want to have like at least 5 queries. Usually what we saw is that if you have like around 5 or more queries for a paragraph, then you can actually move the embeddings to a correct location. But I think one of the things we were saying in our benchmark is like this like huge parallel, which has like 1% of the documents that have like hundreds of queries, and then there is like 99% that have maybe 1 or 0 queries in general. And so in those scenarios, you don't necessarily need like for the entire corpus to have a training set, but you only need a training set for that small proportion that you're actually going to access. And so you can get boost for that part, and if the rest of it you don't get any boost for anyways, it's okay because no one's asking about it that much. So that's one way to think about it. The other way is that if you actually want to improve everything for entire corpus, then you probably want to have around 5 queries. That's like a rule of thumb we saw in our experiment, that around 5 queries per passage is like a reasonable number. Usually works even for like 2 or 3, but 5 was a good number to decide.
Awesome. Yeah, I think that's super insightful. Like, I definitely agree that like a very small percentage of a knowledge corpus gets actively queried very often. So another, I think this is just a clarification question about once you nudge the vectors, then like you're storing the nudge vectors in your vector database so that we can query those nudged vectors rather than the original vectors, right? So would you like to clarify that a little?
Yeah, that's exactly what it is. So you basically just nudge them, and then instead of the original vector, it's just stored at the new vector. And so that's why it requires minimal change to the rest of the pipeline, because you just now have these nudged vectors, which are just new vectors, same as that can be queried the same as original ones. So you just do a basic vector store lookup to query these new vectors.
Awesome. Yeah. This is a slightly separate discussion. Like, I think from my perspective, the idea of personalization for these retrieval system is super interesting. So I think more canonically, some of these, how these are approaches by like having a 2-stage system where you have a general like retrieval layer and then have better customized re-ranking layer for per customer, per user, things like that. I definitely do see this kind of non-parametric approach being one possible way to tackle that as well. I'm curious if there's any thoughts about like sort of general personalization beyond just like a sort of broad adaptation to like a general set of questions.
That's interesting. So perhaps one thing I can see is that you can kind of like, instead of just having generic queries you're fine-tuning your data on, you can kind of just fine-tune them for each user, right? So each user interacts with the system, and then let's say I actually collect training queries for that user, and I only do fine-tuning based on the queries of that user. Now, I think that's an interesting point, because the good thing about nudge is that it's super easy to do and it's like lightweight. So you don't need to store new parameters for the entire like embedding model. You only need to nudge the vectors that this specific user accesses. So it's actually, I think it's possible to do this fine tuning on a per user basis. One thing I would mention is that it actually requires perhaps a slightly different implementation of the approach. So on top of my mind, one of the things that you can do instead of, so I mentioned earlier that you can actually fine tune these embeddings before you put them in vector store, right? So you nudge the embedding, store the nudged embedding in your vector store. The other thing you can alternatively do is that you can actually keep your original vectors in the embedding and then do nudge after retrieval. And that kind of, you can see it as a way to just modify the re-rank, the embeddings after you retrieve. So you can retrieve more, but then you can marginally change these based on this update vector. And so you can kind of apply the nudge after you've retrieved a larger chunk, and then you can do ranking based on this new updated. So I don't know how much it actually makes sense at a physical level, but intuitively, we're kind of saying that you don't need to necessarily apply this to all data embeddings. You can apply it kind of post hoc after you've retrieved some, and then do ranking based on this nudged embedding at query time. But if you go in that direction, then you can potentially do this on a user basis. So for each user, you kind of have these update vectors that you actually retrieve the original vectors, and then for each user, you update them in a specific direction that is denoted by the fine tuning. And so you need to store those update vectors for per user, and then it becomes easy to apply after you treat. I don't know how much that makes sense, but
Yeah, I mean that sounds interesting to me for sure. I I definitely think like sort of
mm,
these kind of lightweight adjustment approaches are more amenable to these like high cardinality personalization. So
mhm.
I was just curious to see if that was part of the consideration as well.
Yeah,
Um,
I definitely agree. I think it's possible to do it, and I hope that someone does it, because it seems like a very natural thing that, as you mentioned, because it's so simple and easy to do, you don't have to spend too much time on it, and so you can just do it for more people.
Absolutely. Yeah. So there was a question about where do we see this nudge approach documented. So there's a paper that is published on arXiv, which I think it should be linked on the Luma invite itself, but we can like send that out afterwards as well. Cool. Let's see. Now, maybe I want to kind of take a very quick small step back and talk about like what led you to think about this particular approach, right? Just obviously there's the motivation for the shortcoming of the existing approaches, but what are some of the other adjacent ideas you've kind of explored and compared, and how you've kind of landed on this particular like non-parametric approach being the promising way to go?
Okay, that's interesting. So, I mean, so I certainly didn't start thinking about the specific thing. So when we started, I think the main broader idea was that if I these systems should get better over time. So if I, for example, if I ask something from my RAG system and it gave me the wrong answer, I
Mm-hmm.
should, and then I told it this was wrong, the next time I ask the same thing, it should give me the correct answer.
Mm-hmm.
Right. So that's like, it's like a basic thing that I just told you it's wrong, like don't do that again. Right. So that was like the general motivation, that what is a good way to bring back feedback into these systems. Um, I think when I started with, I was trying to, and one thing that was kind of clear to us was that this should be like a lightweight approach, because that's the way you can actually plug it into any system. So you kind of wanted it to be easy to plug into whatever pipeline you have. I add this little plugin, and hopefully that helps you take these kind of feedbacks into account. Um, we tried a bunch of different things. So you can, for example, do like very lightweight re-ranking models, and like smaller lightweight, like we had like a basic lightweight decision tree model we built, and a lot of them, they were working, they were like giving us a little boost, and at some point I was like, we should maybe take a step back and see if there is like a more general way to think about this. And so what I like about this approach is that we kind of are looking at like retrieval holistically. We're saying that we have this retrieval, and what are the parts of the retrieval that can be changed? And I think what people had missed is that, oh, if we're changing retrieval, we can actually change the embeddings. The embeddings are part of the retrieval that you can think of them as a parameter. And so I think that was where it clicked, that, oh, if we actually just change the embeddings themselves, turns out things get better. So this was kind of like, we explored a bunch of other ad hoc methods of like, oh, I retrieved a bunch of stuff, and then can I re-rank them? What's the way to do that? And turned out like just modifying the embeddings was the right approach.
Awesome. Yeah, I think that's super interesting. And definitely like the motivation for making the system learn and get better. I think that's what we are all very excited about. I feel like the biggest change from like the older generation of recommender sort of information retrieval is that now sort of we have these more generalized embeddings which give pretty good out of box performance, and then we have more tools in our toolbox to be able to like affect ongoing performance, right? Once you
Yeah.
have additional feedback data. Yeah, and then the observation about like that embedding themselves could be changed. I think that's a very insightful. I definitely haven't seen that too much on the from the other papers. That's why I was like particularly interested in this ideas as well. Maybe just like taking the flip side of this, right? Like, you know, this is a new idea. Like, what would it take for it to be like broadly adopted, right? And what are some of the current sort of pitfalls you might think that's preventing it from being adopted better? And like, what would that look like to be able to overcome those?
So I think one thing I want to mention is that like there seems to be a spectrum between like these non-parametric and parametric methods, or I believe or expect there to be a spectrum.
Mm.
Because so we kind of like these parametric methods, they clearly work when we throw them a bunch of data, right? So we can train the original models with these parametric methods, right? We started with random weights and then we trained them with a large amount of data and they got better to this level we have. And then this with Nudge paper, we are saying that, oh, now you can actually do it non-parametrically. And I think this trade-off and balance between the two is certainly not well understood. I think there is a level, or there's got to be some point you actually need to switch from one to the other. So if I give you a randomly initialized matrix, you shouldn't do nudge on it. You should actually train it first, right? So there is this set of trade-offs between how much training data you have, um, how much compute you have, and so on, that I think that space isn't fully categorized. And I think it's important to be able to say, oh, if you have this number of data sets, then you should this amount of data size, you should use nudge. Then if you have like a lot more, a million training records, then maybe you should go do fine tuning with the pre-trained model. The other thing, so I think there has to be some sort of a crossover between the two as well. That I don't think necessarily that just fully non-parametric is going to give you the optimal way. Maybe there is a way to combine the two. And I think because one of the things Nudge misses on entirely is any possibility of generalization. So because we're not learning model parameters, if you learn a pattern for one specific element, for one specific data record, you're not really generalizing that pattern to other things. Now, in small scales, it's very hard to actually learn patterns. So what we saw is that the fine tuning, the pre-trained model doesn't really do much, because if you don't give it enough data, it's actually not going to learn those patterns at all. So we're kind of like, oh, there's no pattern. You can't learn the patterns anyway. You might as well do something non-parametric. But I think this concept of like, is it possible to bring an easy way to extend nudge to also learn these patterns across documents? So if things are similarly failing, we should be able to somehow try to adjust for that. And so I think that's an interesting direction that I'm trying to figure out how to maybe bring nudge one step closer and kind of bridge the gap between these two, like parametric and non-parametric worlds. So I think this like idea of not knowing the patterns or not learning or being completely oblivious to patterns, that could in some cases not be the best idea. So in some cases, you actually should probably figure out if there is a pattern in how your embeddings are failing you, for example. So I think that's one general direction that I think Nudge needs more work to figure out. And for it to be more widely adopted, I think this whole idea of collecting labeled queries is an important underexplored area. Because we are in this paper, we're assuming that you actually have this set, but the question is how well can you generate it? Does it generalize to what workloads and so on? And so I think that building a proper ecosystem around collecting training queries and labeling them, using language models, for example, to label them, I think that is an important integral part that needs more exploring.
Absolutely. Just to touch on that last point, I think there's a question from the audience about like, what do you feel the impact of synthetic generated queries compared to actual queries? Does that degrade the performance? I'm guessing the answer is depends, but curious to hear how you would elaborate that a little bit.
Yeah, I mean, I think it has a lot to do with how your query workload looks. So I think like one of the synthetic queries, often if you just give it to language model, and I'm guessing there's like work to do, people are exploring how to generate them, and it's like an active area of research, but the most basic way of doing it, you often just get generic queries. And so if your Q&A are generic queries, then it works, right? Like, who was the president of the US? And I'm asking Wikipedia, and so I can generate that query synthetically from Wikipedia. But if I have like more specific queries that somehow aren't as just like basic natural language queries, they're often more complex. There was like one of the benchmarks, for example, we tried on was given an argument, find me a counter argument. And so you have a set of arguments and you want to find counter arguments. Now, generating counter arguments synthetically might not work as well. Or at least requires more effort to figure out what's a good way of doing it. At the very least, you need to prompt engineer to figure out what it should be, right? So it's not as obvious how it is. I think if you have basic natural language questions, I expect like basic like fact extraction natural language question, I expect synthetic queries work. But as the more complex your workload is, I would expect like the benefits to go down.
Yeah. It's all about like the train test gap, right? Like whether if your synthetically generated query is representative of the real distribution of user queries. And then like that could really vary in different domains and use cases. But for like simple fact-finding queries, I would say like synthetically generated, it's a reasonable approximation as long as your prompting is not too bad. Anyways, I just want to go back to like your previous point about the parametric and non-parametric. I think that's a really fascinating distinction, and also like something like I would love to understand a little bit more as well, like sort of the specific trade-off and the decision criteria in which one will perform better versus the other, right? Like for me, like my understanding of nudges is almost like a micro incision or like a nudge, right? Like you need the data to be in already pretty good places, and then you are sort of in a very lightweight way taking in pretty high quality representative feedback to be able to kind of push that a little bit further. What it does seem like is that, like, for example, if you have like a big domain gap between your embedding model and then like your actual thing, then this is not going to work as well. You need to actually fine tune it first, and then maybe like apply a nudge afterwards to act on like specific examples of user query, right? So it feels like a lot more about like this like high fidelity user feedback and trying to get those insight into the retrieval system in a very concrete way rather than like a general adaptation. Yeah, this is awesome. I do think we are at almost the end of time. Yeah, so I think I've been able to go through most of my questions. Like anything else you want to highlight, Sepanta, feel free to use the last couple of minutes to do so.
Nothing comes to my mind. I think I'm generally just excited for this to get used. I think one of the things that I want to see is like we do benchmarks and we don't really get that much feedback of like how this actually helps anyone in the real world. And so I'm hoping that people here can actually use this and see, well, it worked in this setting. And I think, as you mentioned, because it's kind of like a little nudge we're doing, it's also a new method no one has really explored. So I do the limits that I expect the approach has is not necessarily what the limits are. And so I'm very curious to see how it actually ends up getting used. And so if anyone ever tries it out, I would definitely want to hear about their experience and see if it worked or if it didn't work and what was the problems.
Awesome. I think we can wrap that up here. Thank you so much for your time, Sepanta, and for the great presentation
Thanks a
and
lot for
question
having me.
answers.
Very excited to be here. Yep, thank you.
Awesome. Bye.
All right, bye.